Welcome to Module 1, Engineering Thinking and the BAS Method. In this module, we are not starting with software, graphics, or programming tools. We are starting with the way a professional thinks before touching the system. A building automation system controls real physical equipment: air handlers, coils, valves, pumps, fans, sensors, and spaces. When something looks wrong on a screen, the first question is not, "What should I change?" The first question is, what is actually happening in the building, and what evidence do I have? This module gives you a repeatable method for defining the problem, verifying measurements, testing safely, documenting the result, and teaching the lesson back to the organization. This roadmap shows how the module is organized. First, we learn to define the problem clearly. Then we separate observations from interpretations and assumptions. Next, we sketch the physical system so we understand what the sequence is trying to control. After that, we design the smallest safe test and validate the physical outcome. Finally, we document and teach the lesson so the next technician does not have to rediscover the same answer. This is not just a troubleshooting process. It is a professional practice that protects equipment, occupants, time, and credibility. These are the core learning objectives. By the end of this module, learners should not only know the steps of the method, they should be able to apply them in the field. The first objective is to define the problem before selecting the solution. That prevents teams from jumping to a favorite fix. The second objective is to separate observation, interpretation, and assumption. This is one of the most important habits in troubleshooting. The rest of the objectives build from there. Use a repeatable method, think in systems, establish baselines, and recognize when you simply do not have enough evidence to act safely. A BAS workstation can display thousands of values, but it does not know which value deserves trust. It can execute a sequence, but it does not know whether the sequence matches the actual equipment. Engineering thinking is the bridge between the software and the real system. When a value appears on the screen, we ask, where did this value come from? What does it physically represent? And can I confirm it? This habit reduces unnecessary parts replacement, avoids unsafe shortcuts, and improves credibility with engineers, operators, and owners. The statement, "the air handler cannot cool," may be true, but it is not yet useful enough. It does not tell us which air handler, what target it missed, what measurements were observed, which mode it was in, or whether the relevant supporting systems were operating. A strong statement gives another professional a starting point that can be verified. Notice the strong example identifies AHU3, the measured supply air temperature, the set point, the valve command, the reported chilled water temperature, airflow, and operating context. That level of definition reduces guessing and keeps the team focused on evidence. This slide introduces a critical habit. An observation is what we can measure or directly confirm. An interpretation is what that observation may mean. An assumption is something we are accepting without full verification. In the example, the BAS shows a discharge air temperature of 68 degrees. That is an observation, but only inside the BAS database. The interpretation might be that the cooling coil is not removing heat. The hidden assumption is that the sensor value is accurate. A reference thermometer could show the actual discharge temperature is 56 degrees, which changes the entire diagnosis. The BAS engineering method is the core method for this module. It has 10 steps: observe, define, measure, model, hypothesize, test, implement, validate, document, and teach. Notice the order. We do not begin by implementing. We start by observing the condition without assigning a cause. We define the problem clearly. We measure independently when practical. We model the physical system. Only then do we create hypotheses and select tests. After the corrective action, we validate, document, and teach. This is how one problem becomes organizational learning instead of one person's private experience. Before changing a sequence, sketch what the sequence is trying to control. This BAS engineering pyramid reminds us that business outcomes depend on operations, operations depend on controls and data, controls depend on equipment, and equipment depends on physics and measurement. When a space is warm, the local symptom might be a VAV box that cannot satisfy airflow. Upstream causes could include air handler capacity, duct pressure, fan status, filter loading, or chilled water plant operation. Downstream effects might include humidity, pressurization, comfort complaints, or energy use. A simple sketch often reveals relationships the graphic hides. A baseline does not have to be perfect, but it must be defined. If someone says energy decreased by 12%, we need to know the comparison period, weather adjustment, occupancy, operating hours, and measurement method. The same idea applies to a control change. Before modifying a static pressure reset, record fan speed, duct pressure, terminal damper positions, complaints, and energy use. After the change, evaluate the same measures. Without a baseline, improvement becomes a story. With a baseline, improvement becomes evidence. In many field situations, the most valuable first action is not changing the system. It is improving observation. If a loop is unstable, add temporary trend logs before changing tuning constants. If a differential pressure reading seems wrong, verify it with a calibrated instrument before replacing the transmitter. If a valve is commanded fully open, confirm stroke and flow response before rewriting logic. Measurement does not mean doing nothing. It means reducing the chance that your first intervention creates a new problem or hides the real one. Reasonableness checks are one of the fastest ways to find bad data. A value can be mathematically accepted by the database and still be physically unreasonable. If a small chilled water pipe reports 1,000 gallons per minute, the professional should not automatically accept it because the graphic looks clean. We check the sensor range, scaling, units, mapping, and equipment capacity. Related sensors should tell a consistent story. Commands should match feedback. Rates of change should be possible. This is where engineering judgment protects the team from false confidence. The smallest safe test is designed to create information while limiting risk. If we suspect a heating valve is not responding, we do not need to force it fully open for a long period. A better test might be a controlled 10% step with a defined duration, observers, feedback points, and a rollback condition. A strong test distinguishes among hypotheses. It does not simply collect more data. Before testing, define what result would confirm the hypothesis and what result would eliminate it. That makes the test useful and defensible. This case study demonstrates why measurement verification matters. The system appeared to have a cooling problem. The BAS showed supply air around 62 degrees with the cooling valve at 100%. A quick response might be to blame the valve, coil, plant, or airflow. But the independent thermometer measured about 56 degrees at the discharge sensor location. The sensor resistance also corresponded to about 56 degrees. The root cause was not chilled water flow or coil performance. It was the controller input configured for the wrong thermistor curve. The right correction was to change the input configuration under Change Control, Validate, Document, and update the as-built point schedule. These common mistakes show why disciplined thinking matters. Many teams open the programming tool before they define the physical problem. They trust graphics because they look professional. They treat an alarm message as the root cause. They change several variables at once, which makes it impossible to know which action helped or hurt. Managers can unintentionally encourage this behavior by rewarding speed more than evidence. A stronger culture rewards clear problem statements, safe tests, permanent corrective action, and documentation that helps the next person. This knowledge check is designed to reinforce professional sequencing. The correct answer is C. Verify the measurement and define the physical problem before intervention. The valve may be failed, but the data does not prove that yet. The BAS temperature point might be scaled incorrectly, installed in the wrong place, or reading a stratified airstream. Lowering set points or replacing the actuator before verification can waste time and introduce new problems. Disabling the alarm hides the symptom instead of solving it. The professional response is to separate observation from interpretation, verify critical values, and then design a safe test. The practical assignment asks learners to use the method rather than memorize it. They should select a real or sample BAS problem and complete the engineering investigation worksheet. The work must include a precise problem statement, separate observations, interpretations, and assumptions, a physical sketch or system description, at least 2 hypotheses, the smallest safe test, acceptance criteria, rollback conditions, validation evidence, and a short lesson learned. This is the type of document that can improve team practice and reduce repeated failures. This module introduced the thinking process behind professional BAS work. The major habit is simple but powerful. Define before you fix. Separate what you know from what you think and what you are assuming. Sketch the system. Verify measurements. Choose tests that are safe, bounded, reversible, and informative. After the correction, validate the physical outcome and document the lesson. In the next module, we build the measurement foundation. We will look at units, dimensions, accuracy, precision, resolution, false precision, and uncertainty. Those concepts determine whether the numbers in the BAS are good enough for the decisions we want to make.